Okay, this is Dr. Brown. In this video, we are going to begin to look at various differentiation rules. I think you all know that the derivative of a function, f prime of x, is the limit of, as h approaches 0, of f of x plus h minus f of x divided by h, if this limit exists. We are going to, over the next couple of weeks or so, look into the derivatives of all kinds of functions that you've already studied, and now you're going to understand how to calculate the derivative of these functions. And the very first function we're going to look at is probably the simplest of all. In fact, we said at the very beginning of this class that if nothing ever changed, you really wouldn't need differential calculus. Well, the first function you see here is the function f of x equal y equal a constant. Just by looking at it, you realize that f prime of x is equal to 0. Now, I'm going to introduce another slightly different notation. You already know that f prime of x is the derivative sometimes we write that as y prime. And now we're going to introduce the terminology d dx of whatever is in parentheses. And what is in parentheses would be a function, generally. D dx means the derivative of whatever is in parentheses with respect to x. And you'll recall that when f of x in the previous video was 1 over x, that f prime of x was minus 1 over x squared. So we would say d dx of 1 over x is minus 1 over x squared. So on this simple constant function, we have really our first simplest rule, that d dx of a constant is equal to 0. Now, you've seen me sort of hint around that the derivative of x to the n is equal to nx to the n minus 1. This is called the power rule. And we're going to show that for n being an integer, that this is indeed so. In fact, it turns out it's also the case if n is a rational number or an irrational number. The formula still works. Now, to do this calculation, we must do this. If f of x is equal to x to the n, Now we've already done this, as you know, for n equal 1 and n equal 2, and some of you have done it for n equal 3. We have to calculate f prime of x is equal to the limit as h approaches 0 of f of x plus h to the nth power. Notice that's f of x plus h is x plus h to the nth power. Then we subtract off f of x and divide by h and try to calculate this limit. Now, to prove this, we're going to use the binomial theorem. I'm not going to go over the binomial theorem extensively with you. Some of you have seen it. I'm just going to use the results of it. You may recall that if you have a plus b to the nth, and you've done this obviously for n equal 1, n equal 2, and n equal 3, and possibly even n equal 4, you could just multiply it all out. But the binomial theorem says that this can be written as a to the n plus n a to the n minus 1 times b plus 1/2 n times n minus 1 times a to the n minus 2 times b squared. Notice every time the power of a goes down, the power of b goes up by 1. And then you just add all these up, dot, 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 look at all the terms. And you get the last two terms would be n a b to the n minus 1 plus b to the n. I think you figured out that it was going to start at a sub n and end with b sub n. This is a binomial theorem. Notice that all of the coefficients of a to a power and b to a power are all constants determined by whatever n is. So if we want to calculate x plus h to the n, in other words, we let a equal x and b equal h, and we can calculate what x plus h to the n would be, and that becomes x to the n plus n x to the n minus 1 times h plus 1/2 n times n minus 1 x to the n minus 2 h squared plus dot 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 plus n x h to the n minus 1 plus h to the n. Now we can plug in and see that limit as h approaches 0 of x plus h to the n minus x to the n divided by h is equal to the limit as h approaches 0 of x to the n plus n x to the n minus 1 times h plus 1/2 n times n minus 1 times x to the n minus 2 times h squared plus dot 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 plus n x h to the n minus 1 h to the n minus 1 plus h to the n minus x to the n. Remember, we have to subtract off x to the n, and we divide all this by h. Now, let's give myself a little bit more room, and let's see what's happening. As you have seen in all the other examples, x to the nth power is going to be canceled out by minus x to the nth power. And notice that every other term has h or h squared or h cubed or h to the n as a factor. So you can easily see that this is a limit as h approaches 0. This h will cancel with that h, and you'll have n x to the n minus 1 plus 1/2 n times n minus 1 x to the n minus 2. Instead of h squared, you'll have h because one of the h's cancel, plus dot 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 plus n x h to the n minus 2 plus h to the n minus 1. Notice that this h will cancel out one of the h's and the h to the n. So notice as h goes to 0, the only term that doesn't have h in it is this term. All of these other terms go to 0. And so f prime of x is equal to n x to the n minus 1. This is called the power rule. You'll be using this a lot. So d dx of x to the n is simply whatever the power is, n times x to the power minus 1. And I am sure everyone here will know this and use this very well. This is probably one of the most important differentiation rules that we'll be talking about. Now let's just do some examples. In fact, if you all want to pause the video and try to do every one of these right now, feel free to do so. Then you can come back and look at the answers. Okay, if you're back now, d dx of x to the 5th, it's just going to be the power 5 to x to the 5 minus 1 equal 5 x to the 4th. For number B, d dx of x to the 4/5 power is going to be the power, which is 4/5 x to the 4/5 minus 5/5, which is of course minus 1, and that is equal to 4/5 x to the minus 1/5. And if you wanted to, you could write that as 4/5 or 4/5 x to the 1/5 power. In other words, you could put the positive power down in the denominator. Now, as we said, the n could be an irrational number like pi. So d dx of x to the pi power is going to be the power, which is pi, x to the pi minus 1. And that's the answer. Notice that to do 1 over x to the 5th, you have to do this, d dx of 1 over x to the 5th. You need to have x in the numerator. So that would be d dx of x to the minus 5. So the power is minus 5, and remembering the rule, d dx of x to the n is equal to nx to the n minus 1. We put minus 5 in front, then x to the minus 5 minus 1 equal minus 5 x to the minus 6. We could leave it like that, or we could make it 5 over minus 5 over x to the 6. Finally, number E, d dx of x to the 2/5 is going to be 2/5 x to the 2/5 minus 5/5, which is going to be 2/5 x to the minus 3/5. Or you could write it as 2/5, 2 over 5 x to the 3/5. Now on the next page we got another rule called the constant multiple rule, and we've already talked about this a little bit. It simply says if you have a function u, here u is equal to some function of x, that taking the derivative of c, where c is a constant, times the function, you just multiply c times the derivative of the function. So this simply says that d dx of like 10 f of x is equal to 10 d dx of f of x. And this means that if you want d dx of like 10x to the 4th, it's going to be 10 times 4 x to the 3rd power equals 40 x cubed. And there are going to be all kind of examples we'll be looking at. Just to illustrate this a little further, suppose we have the function here in yellow, y equal x squared, and we look at the point 1 and 1. D dx of x squared is equal to 2x, and the slope at x equal 1 is 2. Then let's look at the function y equal 3x squared. d dx of y, or equal d dx of 3x squared, is equal to 6x. And so at x equal 1, d dx of y is equal to 6. So when you multiply one function by 3, its derivative is going to be 3 times as great. Now, this derivative sum rule is very easy to prove. We're not even going to spend any time on it right now. It just simply says that if you take the derivative with respect to x of the sum of two functions, u plus v, you just simply take du dx plus dv dx. Real simple example, d dx of 5x cubed plus 2x to the 7th power. You just do each one at the time and you get 15x squared plus 14x to the 6th. It's just as simple as that. That's the derivative sum rule. Looking at an example, here's one with 4 terms. The derivative of x cubed is 3x squared. The derivative of 4/3 x squared is going to be 2 times 4/3 times x. And that ends up being 8/3 x. The derivative of minus 5x is just going to be minus 5. And then, of course, the derivative of 1, which is a constant, is 0. So the answer is 3x squared plus 8/3 x minus 5. Now, we're going to look at a function that's really the sum of 3 functions, a 4th order, a 2nd order, and a constant. And we're going to work a slightly different problem here. The question is, does this curve have any horizontal tangents? A horizontal tangent means that the d dx of the function is 0 at that point if it has a horizontal tangent. So let's take d dx of x to the 4th minus 2x squared plus 2. That's simply 4x cubed minus 4x using the power rule. And now we want to set this derivative equal to 0 to see if it has any horizontal tangents. Well, we have the equation 4x cubed minus 4x equals 0. Factoring 4x out, we get 4x times x squared minus 1. And we can further factor it into x plus 1, x minus 1 equals 0 if you want to, or just by inspection see that the zeros are going to be 0, 1, and minus 1. So we believe that this function has horizontal tangents at x equals 0, x equals 1, and x equals minus 1. And at x equals 0, the y value is 2 by plugging in the original function. Plugging in x equals 1, you see y is equal to 1. Plugging in x equals minus 1, you see y equals 1. And if you graph this on your calculator, you see this 4th order polynomial, and indeed you find that it will have horizontal tangents at these points that we calculated. Now, we're going to get into an even more interesting derivative, the derivative of an exponential function. And an exponential function, as you recall, is f of x equal a to the x, where a is the base. Examples are 10 to the x, 2 to the x, e to the x, you can have just about any kind of positive base that you can come up with. You could have pi to the x, where pi is a base. Now, to do this, we're going to use the definition of the derivative. So f of x plus h is equal a to the x plus h. So the derivative is going to be a to the x plus h minus a to the x. And notice a to the x plus h is equal to a to the x times a to the h. And notice you can factor out a to the x and have a to the x, which is the function itself, times a to the h minus 1 over h, calculating the limit as h approaches 0. So we see that the derivative of a to the x is going to be a to the x itself times whatever the limit of a to the h minus 1 divided by h is. And of course this will depend on a. But whatever that number is will be a fixed number. Okay, looking at the fact that the derivative of a to the x is equal to a to the x itself times the limit of a to the h minus 1 over h, we have on this page a graph of a to the h minus 1 divided by a versus h for various values of a. As you can see, that if a is equal to e, that the limit is 1. And of course the limit happens to be other values for various values of a. So at the moment, what we're going to show you is that d dx of e to the x equal e to the x. This is the only function whose derivative happens to be itself. So d dx of e to the x is equal to itself. Later on we will have equations for derivatives of other exponential functions, and we'll see what they are. But for now, all you need to know is the derivative of e to the x is equal to e to the x. Now, another very important rule is going to be the product rule. And it simply says that if you want to take the derivative of a product, u times v, there is a rule that says you take the first and multiply it times the derivative of the second, and then the second and multiply it times the derivative of the first. In slightly different notation, if you have the derivative of f of x times g of x, it's going to be the first times the derivative of the second, which is g prime, plus the second times the derivative of the first. So let's just show this example. Here we have a product of two functions. The first is 1 over x. Notice that d dx, the first, which is d dx of x, d dx of 1 over x is going to be d dx of x to the minus 1, which is minus 1 x to the minus 2, which is minus 1 over x squared. So that's the derivative of the first. So let's use the product rule. And so the derivative of 1 over x, which is the first, times x squared plus e to the x, which is the second, is going to be the first, which is 1 over x, times the derivative of the second. Well, notice the derivative of the second is 2x plus e to the x. That's because the derivative of e to the x is itself e to the x. The second part of the product rule says the second times the derivative of the first. Well, the derivative of the first is minus 1 over x squared. So now, multiplying out 1 over x times what's in parentheses, we get 2 plus e to the x over x squared times minus 1 over x squared is minus 1. And then you get minus e to the x over x squared. And finally, you get 1 plus e to the x over x minus e to the x over x squared. And if you factor out e to the x over x squared, you get x minus 1. Just multiply this out and you'll see that you will get the same as this. So this is the answer to the derivative of the product. Now, sometimes you may not want to use the product rule. You might want to just multiply everything out first and then take the derivative. Notice in this function you got the product of two functions. If you use the product rule, you got the first, which is x squared plus 1, times the derivative of the second, which is 3x squared, plus the second, which is x cubed plus 3, times the derivative of the first, which is 2x. Now, to simplify the answer, you distribute the 3x squared into the x squared plus 1 and get 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x. Combining like terms, you get 5x to the fourth plus 3x squared plus 6x, and that's the answer. Notice you could have chosen to multiply out before taking the derivative. Doing that, you get the first, which is x to the fifth, plus the inside is x cubed, the outside is 3x squared, and the last is 3. Now take the derivative of each of these functions separately, and you get 5x to the fourth plus 3x squared plus 6x, which actually took fewer steps than using the product rule. However, this will not always be the fastest way, but very often if you're multiplying polynomials together, it may be easier to multiply first and then take the derivative. Now, the next rule that we're going to look at is called the Quotient Rule. And this is where you have one function divided by another function. And that rule says that the derivative is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And this notation, d dx of f of x over g of x, again is sometimes I call it the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the denominator or bottom squared. This is a quotient rule, and you'll be using this a lot. Now, we got two examples here. The first example is y equal t squared minus 1 over t squared plus 1. The rule says it is the bottom, which is t squared plus 1, times the derivative of the top. Well, the derivative of the top is just 2t, minus the top, which is t squared minus 1, times the derivative of the bottom, which is 2t. And then you take the bottom squared, which is t squared plus 1 squared. Now, multiplying this out, you get 2t cubed plus 2t minus 2t cubed plus 2t. The t cubed terms cancel, and you get 4t divided by t squared plus 1 squared. So this is the answer for the quotient rule. Now, we know that d dx of e to the x is equal to e to the x, but d dx of e to the minus x is not necessarily equal to e to the minus x. In fact, it's not. And we're going to use the quotient rule to show what it really is. Notice that y can be written as 1 over e to the x. Now, we know the derivative of 1 a constant. We know the derivative of e to the x. So we can use the quotient rule to take the bottom times the derivative of the top, which is 0. The derivative of the constant is 0, minus the top times the derivative of the denominator, which is e to the x, divided by the denominator squared, which is e to the x quantity squared, which is e to the 2x. Now, that means we've got minus e to the x over e to the 2x, which is equal to minus 1 over e to the x, which we can then bring the e to the x up to the top and get minus e to the minus x. So our result is that the derivative of e to the minus x is minus e to the minus x. Now, here's an example in which maybe you don't want to use a quotient rule. You want to multiply things out first and then use the power rule. Notice if you use the quotient rule here, you got a pretty messy numerator, a fairly simple denominator. But notice, if you go ahead and FOIL out the numerator, you get that the numerator is equal to x cubed minus 3x squared plus 2x divided by x to the fourth. Dividing x to the fourth into each of the three terms at the top gives you x to the minus 1 minus 3x to the minus 2 plus 2x to the minus 3. And notice you have three terms here. You can use the power rule on, and that gives you minus x to the minus 2 minus 3 times minus 2 x to the minus 3. And the power rule on the last one it gives you minus 6 x to the minus 4. And so rewriting that with positive exponents gives you minus 1 over x squared plus 6 over x cubed minus 6 over x to the fourth. And the last thing we're going to talk about is that you can not only have first derivatives, but you can have second, third, fourth, and you can keep on taking derivatives. So if you take the derivative of the first derivative, you got the second derivative. If you take the derivative of the second derivative, you got the third derivative, and so forth and so on. And there are various symbols for doing higher order derivatives, which we're not going to really focus on a lot, but we will talk about this later. Let's take a very simple example of a cubic function and take the first four derivatives. And taking the first derivative, we get 3x squared minus 6x. The derivative of 2 is 0. Taking the derivative of the first derivative gives us 6x minus 6. And then taking the derivative of the second derivative gives us 6. And finally, taking the derivative of the third derivative, which gives us a fourth derivative, shows that the fourth derivative is 0. And that is it.